So now coming back to your synchronous machine, if your machine is initially unloaded and you're basically operating at synchronous speed with constant field current, and suddenly you apply a three-phase short circuit at the terminals of the generator, basically you will find that the current in the three-phase armature will respond to in the way that we are showing in figure 4. Okay, so you'll find that your stator current, which is a sinusoidal current, will basically start at a very high amplitude, and as you basically operate a few cycles, you'll find that the amplitude of the sinusoidal current reaches a steady state value, which is basically A, right? And the initial subtransient period is basically at a very high value, which is, if you look at this envelope here, it's basically reaching something around the value C. And from the subtransient, it basically decays to a value of what we call D here. And this value during the transient period is projected onto the value B there, right? So these three values, so A, B, and C, are basically the projected value of your amplitudes in each of the period. So you'll have the sub-transient period, then you have your transient period, and then the steady state value. So in our initial cases that we've looked at in Machines3, we were basically working, as you know, with the steady state value. And also in some cases, we've looked at the transient reactance, which basically looking at the value of B. So this is the first time we're showing the subtransient reactance, which we will discuss a bit later in this section. And so what you need to basically observe in this figure 4 is that you have three sub-period. You have the subtransient, the transient, and the steady state period, where the amplitude of your armature current is going to change. It's basically amplitude. Right. So the way that your amplitude is changing is basically based on the currents that are induced in the stator winding, right, following the fault, and also how does the flux in the stator and rotor interact during each of the three different period. So when your machine is operating in the steady state value, basically the amplitude of your armature current is determined by what we call the synchronous reactance of the machine. Okay, so the synchronous reactance of the machine will determine this value of A here. That is the amplitude of the stator current at steady state. And in this subtransient period, the currents basically are induced in what we call damper winding cages of the synchronous machine. And because they have relatively low inductance, right? So the current in these windings decay to zero very fast. So the behavior of armature current during the transient period, right, is governed by the inductance, or more precisely the time constant of the field winding which is much larger than the inductance of the damper winding. Okay, so this explains why you will find that the transient period is much longer than the subtransient period. Okay, so the transient period ends with the transient current in the field winding basically decaying to zero, and the change in the field current resulting from an armature short circuit is shown, as I said, in figure 5. So this is very similar to what we've observed earlier. You will see there. So the behavior of your field current following a short circuit fault is very similar to the case we've described earlier in figure 3. You'll find that field current rises sharply in reply to the magnetic flux created by the armature current, and then it basically decays back to zero, back to its initial value. Okay, so if you look at the distribution of flux between the rotor and the stator between those three distinct periods, so we have, this is the first one is your steady state period. You'll find that the flux is linked with the stator ion and the rotor ion, right? It's well distributed, and this is along the D axis and this is along the Q axis. You find that the rotor circuit is basically participating in the flux path of the machine, and in the subtransient period, you find that the flux now is mostly passing in the stator ion and slightly along the rotor surface, right? So it's not participating fully in the rotor surface of the machine, and this reactance obviously is different from the reactance due to the steady state value, right? So the transient reactance is slightly lower than that of your steady state value, and you will find that obviously then the current due to this transient reactance is a little bit higher because of the lower value of the subtransient reactance. Now, if you look at the this is the transient reactance. This is this transient period here. So the last case is the subtransient here, and as you can see here, this is the initial case. So as soon as you apply the fault, this is the way the flux is distributed. So as you can see now, it's not passing along the rotor surface at all. It's mostly concentrated in the stator ion. Okay, so what happens because of that is the reluctance of this ion is obviously much lower as compared to when the flux is passing slightly through the surface of the rotor. So obviously here the reluctance is much lower, and obviously the subtransient reactance is much lower, and that basically results in this much higher current that you're observing in this figure 4 here during this period here. So the amplitude of your armature current is much higher here because of, you see, the distribution of flux is mostly along the stator ion, and obviously the reluctance is much lower. So now, to fully understand why one should make a distinction between subtransient and transient period, one should have a look at the magnetic distribution, as I said. And obviously, during the subtransient period, you will find that the currents induced in the damping cages do not allow the armature flux to penetrate the rotor pole shoes, as I've shown in the figure there, figure 6. And when these current decay to zero, the subtransient period is over. Okay, and during the transient period, you'll find that the reaction of the increased field current prevents the armature flux from penetrating the rotor, but not the rotor portions. So the magnetic flux of the armature reaction can fully penetrate the rotor only when the transient period is over, and that's during the steady state operation. So this basically this um, behavior of your field current, okay, determines why your flux lines are basically either passing through the rotor circuit, or it's basically being, you can see during the transient period is just passing slightly through the pole shoes there and going out, whereas when it's doing the subtransient here, the because the current induced in the field circuit now is basically opposing that one, the flux on the stator, and obviously then it passes through the stator ion. Okay. Right, so we'll look at a general case now with the symmetrical waveform of the armature current that we looked at in figure 4. Basically, if we look at the effect of applying a certain transient short circuit to the armature, and if so, basically, if you look at, let's go back to this figure, this response of the armature current with respect to with time following a short circuit fault is a very special case where, as you can see, the armature current is starting, so the fault is applied exactly at the point where the armature current was at 0. Okay, the amplitude was 0. So if you look at a practical case, you'll find that the fault can apply at a different time sequence. Okay, so at a different time period, if you apply a short circuit fault, then the response of each of the armature current on each phase will be different from what we've shown in figure 4, right? Because the initial value of the current will be different. It will not be 0 at that time when the short circuit is applied. So the magnetic flux produced by the field winding links with the armature windings, and when the three-phase short circuit is applied, right? So these flux linkages are proportional to, so each phase A, B, and C, are proportional to the cosine of theta, right? Where theta is the angle between the axis and the axis of phase A. So that we've discussed earlier when we were presenting the DQ model of the machine. So we're saying that the flux linkages in each phase is proportional to the cosine function, right? So so obviously then the flux linkage of each phase is different, right, at the time of the application of the short circuit to the machine. So if the flux linkages are different, right? So according to the principle of your constant flux linkage, the flux linkage is determined by these three set of equations. They must be maintained after the application of the short circuit. And this implies that each of the short armature current will contain a DC component, right? And the flux linkage given by equation 3, so those three sets are not time dependent. So let's look at figure 7. And having a close look at the DC components of this current, it is obvious that the short circuit was applied when the angle theta was 180 degrees. So let's have a look. Right, so as you can see here, if you look at the response of the armature current with time when the fault was applied, you can see that now it's basically rising and reaching a certain steady state. So phase A was in its negative cycle. Phase B was basically just starting its positive cycle, and phase C was just about to reach its peak, and then it was going into the positive cycle. So this is your envelope that we were discussed, right? And the DC component, as you can see, is basically represented by the dotted line here, right, for each phase. And this is the response of the field current. So it was initially at um, IF naught. So it rose to a high value, and then it's settling back to basically coming back towards IF naught if you basically extend the simulation. Okay, so the DC components of the armature current produce a stationary magnetic flux, and this means that the field winding rotates with respect to the flux at the synchronous speed. So this results in the AC current of the fundamental frequency, usually 50 hertz for South Africa, superimposed on the field current as shown in figure 7. So that's the one we're showing here for the field circuit. Right, so this was basically the response of the 3 armature current. So in your assignment, you'll be required to basically simulate the machine and show the response of the armature, basically with respect to a short circuit fault as shown here. So you'll have to show phase A, B, and C, same like that, and how how is it changing with respect to time until it reaches steady state. So all that you'll have to basically demonstrate in your assignment. Now we will look at now how to determine the short circuit current, right? So initially, if the machine is unloaded, the armature short circuit current can be determined for various periods using the appropriate reactances as we discussed. So that will be your subtransient reactance, then your transient reactance, and then your steady state, which is your synchronous reactance. So during short circuit, these magnetomotive forces will basically act along the d-axis, and the equivalent circuit for the various short circuit are shown in figure 8. Right? So as we've shown in the previous course, so your equivalent circuit will depend on the time interval of the transients that follows the short circuit. So at the moment when the fault is applied, basically we will have what we call the subtransient period. So that will be XD double dash. Okay, and then so to get the current that's flowing in the circuit, basically you're going to take you're going to use the reactance X double dash, which means the subtransient reactance. And the next stage, once that's over, you'll reach what we call the transient period, and here you'll use what we call the transient reactance given by XD dash, right? And finally, the steady state we will use what we call the steady state reactance, which is your d-axis synchronous reactance. So that's xt. So 3 different equivalent circuits for each of the time period that your machine experiences the short circuit. And how do you determine these values of the d-axis synchronous reactance is given by equation 4, 5, and 6. As you can see, it relates to that those points that we were pointing at on the curve. So OA, OB, and OC, and will basically determine the value of your transient reactance, or your subtransient reactance, or your steady state reactance. So equation 7 is basically giving you the total effective short circuit current of the armature for each of the time period. Okay, so you'll have 3 different time period there. So one will be TD naught dash, then you'll have TD naught double dash. So one is for transient period time constant, one is the subtransient period time constant, and then you'll have TA, the last one here, that's the armature time constant, and that determines the decay of the DC component. So the largest DC component occurs in a phase current when the flux linkage of that phase is maximum when the short is applied. So the largest possible DC component is equal to the initial amplitude of the subtransient current. So that will be equal to, so di DC naught max will be equal to square root times EF over X XD double dash. Okay. So as we've discussed, so we'll have 3 different equivalent circuits for each of the different periods, and we will also have, as you can see, the voltage that's behind your subtransient, your reactance is there, whether it's transient or steady state. So that value of EI, it will change. So you have EI dash, and EI double dash. So one is the voltage behind the subtransient reactance before the fault. Then you'll have the voltage behind the transient reactance before the fault, and the voltage behind the synchronous reactance before the fault. So equation 12, as I said, is basically showing you how you can work out the short circuit current. And equation 13 is showing you how you can determine those time constants. So as you can see, the time constant TD dash double dash and TD dash, those ones they appear in the equation for your short circuit current, equation 12. And how you determine them, you use equation 13, and equation 14 you use them to get the maximum DC, the value of IDC naught maximum. Okay. So typical values for XD dash, and X double dash are shown here. As you can see, those reactances drops quite drastically, and obviously that causes your short circuit current at the subtransient period to be much higher compared to the steady state value. And the time constant is telling you basically how long is those subtransient period, or the transient period, and the time constant for your steady state period. So let's look at a worked example. So this machine is initially operating at unity power factor and operating at rated load, rated kVA, and rated terminal voltage, right? So obviously, if the generator operates at unity power factor, rated load, and rated terminal voltage, obviously you know that it's operating at a terminal voltage of 1 per unit, and obviously the power per phase will also be 1 per unit, and that will give you a current also of 1 per unit. Okay, so the value of xd, xd dash, and x double dash is given, right? So you're asked to determine the initial value of the subtransient component of the short circuit current, right? So let's have a look here. So as I said, the equivalent circuit of the generator basically for each of these period will be different, right? So when your machine is operating at basically the steady state value, right? So EI is given by VT, so IA then JXT, right? So that is the vector form, and the magnitude of this voltage then, you're going to take square root of VT to the squared plus IA times XT to the squared. Okay, so if you look at, as we looked at the data provided in the question, it's unity power factor and it's operating at rated, as I said, power and terminal voltage. So, and that will give you a rated also current of 1 per unit. So all these values here, if you enter them in the equation, so you'll have 1 per unit for the voltage, 1 for the current, and XT, as you can see, is also 1 there. So when you substitute here, you'll find that you'll end up with 1 plus 1 here will be 2, and that's square root of 2 per unit for EI. So that's the voltage behind the steady state value of your synchronous reactance, which is XT. Okay, so now you extend the same equation here, basically to include the transient period and the subtransient period. So what will only change here is the value of XT. So in the second equation, to get EI dash, you basically change XD into XD dash there. And then to get EI double dash, you change the reactance into XD double dash. Right? So you're going to substitute those values here. So you have been given XD dash and X double dash. So you substitute them here, and that will basically allow you to determine the voltages behind the reactances prior to the fault being applied. Okay, so the reason why we are determining these voltages is we want to draw the equivalent circuit, those equivalent circuits for each of the transient period. So you'll have your subtransient, your transient, and your steady state. So we're determining these voltages, okay, and then we can determine the value of the short circuit current. So you can see there, basically to obtain the value of the short circuit current, I double dash. So you can look here back into the equation. So as you can see, you have those components, 1, 2, and 3 there, right? So we're going to use that to basically determine I short circuit the current for the subtransient period. So this is EI double dash over XD double dash minus EI dash over X dash XD dash. Okay, so we're looking at this value here, right? So this term here. Okay, so this term is basically giving you the initial value of the subtransient short circuit current. Okay, so I short circuit double dash naught. You substitute those values there and you can work it out. Then for the transient period, you work out I short circuit naught dash. So basically you're going to use this term here, this one. Okay, so this is how you work it out, and you substitute the value. You can see that's 5.98 per unit. And then for steady state, so you end up with only the first term, which is here, EI over XT. So that will come out to be EI over XT. So we worked out EI as root 2 over 1, that's square root of 2 per unit. So the maximum DC offset, so we'll use that equation here, the one here. So that value comes out to be 11.87 per unit. Okay, so just to get familiar with this analysis of transients, so what you do is I will upload the tutorial question with the equations you require for the short circuit to work out the short circuit current. So please go through the example and try to solve the example yourself, and then please attempt the tutorial question, and then we can meet at the next session on Friday to go through the tutorial solution. Also, please remember on Friday we will have the test for the two sections that I've mentioned on the course outline. That we will basically have the test at 10:30 for that section. Okay, guys. So we'll stop here for today. And also, if you have any question, please unmute and you can ask your question.
Sorry, sir.
Yes.
Okay. Well, for the test on Friday, is it possible to move it to the first period lecture?
No, I can't, because it will clash with the other students that having a clash. So I will have to run it at 10:30. I will have to run it.
The reason being is another lecturer for third year module has scheduled a test at 10:30 as well. I emailed him and he refuses to move it as well.
So can you just email me and then we'll take it from there for your case?
Okay, I have sent you an email though last week.
Okay.
So I'll
just remind me. Just send me an email about that, and I will we'll deal with that one together. Okay.
Okay. Thank you.
All right. Any other question you have? Okay then. So we will end this session now, and so we'll meet on Friday for the initial period. We'll have a short tutorial, and then we'll have the test at 10:30. Right. Thank you very much.